Hey everybody, I'm here for day 14 for Advent of Code 2023. This one will be a little later in the day. I had a lot of busy stuff at work happen, and I wasn't able to get to it. Uh, the part two problem also took a little bit of time for me to think about. My anyway, we'll talk about it, but um, it. I just want to say that, first of all, I very much appreciate all the people that are commenting and are watching my videos. Um, it's cool that people are interested in the stuff that I'm doing. But I also appreciate, if you have something you'd like to say to maybe improve my code, I would love to see that as well. Right? I don't always get it perfect, and maybe there's some more interesting, better way. So if you've got your own solution or some way to optimize something, I'd love to hear from that as well too. The way that I thought we could do it is I'll try and start posting these in the Reddit mega threads. Well, I have been, but maybe you guys can just look for them there. So if you're part of Reddit, there's an Advent of Code thread or subreddit, I guess is what it's called, and they every day they do a mega thread for all the solutions, and you can look for mine. It's the same as my YouTube handle, iCubed, ICUB3D. You can tell me, share yours, share your solution with me, or maybe ways to improve my own if you want to look at the code. Obviously, I link my stuff down below as well. But given all that, let's get started. So here's day 14. The idea was you are given a grid like this, a little map, and that grid contains O's, the letter O. Just to be clear, it's the letter O, which are rounded rocks. The hashtag, which is a cube-shaped rock, and these dots, which are like empty spaces. And the idea is the round ones can roll, the hash ones can't. And for part one, at least, what they want you to do is just roll it north. So imagine you have the board like this. You're going to tilt it like this, and all the round rocks should slide to the north, right? So that is probably not too big of a problem, not too hard to do. You can imagine it like maybe I can go over here and show you, like, you can kind of imagine the case where, if you're looking at this rock, it doesn't have to go anywhere north being up, because it's already as far as it can go. The same with this one, right? This one, though, could be pushed up to this position right here, and this one could be pushed up to this position. So now you have round rocks right here. This one could be pushed up to this position right here, but it would stop when it gets to this point. This one would go all the way up to here. And notice these two. This is something to particularly pay attention to when you're, especially when you get to part two. Right now, you're just rolling north, but in part two, you start rolling in other directions. Like, if you don't do it in the correct order, if just visually looking at it, it's pretty clear that this one, and this one, all three of these should roll up and eventually be right here, right? In these three places. So this one would go here, this one would go here, and then this one up here would go right here, right? They're all going to roll up together. If you had done it in a wrong order, you might, like, for example, if you happen to visit this rock first and say, hey, okay, start rolling up, and you run into this one, you may think this one is done, but it's not actually. This doesn't, because most people will iterate going from here to the right, and then, by row and then by column. If you're starting at this initial position, you won't run into it when you're rolling north, but you would if you're rolling, like, say, south, for example, right? If you hit this position and you're rolling south, you'll hit this. And so when you're, just that's something to keep about when you're doing part two. The idea is make sure you're rolling in the right order, but otherwise the algorithm, at least in your head, is relatively simple, right? Is like, look at my current position and then roll up until I can't roll anymore. And for that one, that's here. And so what happens is, what they say is, okay, you do all this rolling, and eventually you end up with a grid that looks like this, right? I can't really show them both on the screen at the same time, but you can see, like, here's the original, and all these have now moved up. They've all kind of moved up to the top. And what they want you to do for part 1 is to calculate the total load of all of the round rocks. And the way you do that is you get points for how far they are from the south. So these are 10 away, so these all get 10. So the 10, 20, 30, 40, 50 in total here. These are 9 away from the south. The way you calculate that, right, is just the, we'll say like the grid len minus your current Y position, right? So imagine you're right here, your Y position is 0, 1, 2, 10 minus 2 is 8 is the way to think about it. So you'll see that in a minute. But that's part 1. Let me clean this up a little bit so we can use it later if we need to. How does that look in code? Well, let's just start with parsing. The parsing again this time was not too difficult. It was just a vec of cars because you can, it's relatively easy just to like look through the grid and you're just manipulating a grid, right? So there's not much to it. There's no need to like track state and movement and direction and stuff. So I didn't need to use nom or anything special like that. I just said, okay, for each line, take all the characters and make them an array and then collect those into an array. And now I have a grid. And so then what do I do in part 1 is pretty easy. I want to loop through all of the grid. And if I ever find a position, call this P1 roll north function. And all that does is just what we talked about here, right? Is so I'm going to loop through all of these, find one, and say, okay, I'm at this position, so now I can roll. I'm going to roll it north until I find it. For part 1, that actually returns the value. Remember, I said like once, say I've moved it to this position, I know that its Y position is now 2, right? The Y equals 2. So this one is moved up here. I know its Y equals 2, so I can just do grid len minus 2, which would be 8 in this case, so its value is 8. I can calculate that as I'm moving it, and so that's why I have this total here for part 1, is I'm just saying, okay, I'm going to keep track of the total as we go. Every time I find one, I'm going to roll it, but also return its final Y value, the total value, and add that to the total, I should say. It's just like a shorthand. You could imagine an algorithm, and you'll see later in part 2 I use it, where instead of tracking this total here, you just call roll north for each one you find, and it moves them all up. And then you call like a get total load, and it just loops through all of the positions and finds them and calculates them based on that. So this was just a shortcut. Instead of doing 2 iterations over the grid, I only do 1. That doesn't really save you a bunch of time, but I just saw it as I was doing part 1, so I did that. So what does the roll north function do? First, again, since we want to know its final Y position, we're going to track that position right here so that we can calculate the total load, right? After we've moved it all the way up, which is this right here, we can then calculate its total load by doing grid len minus its current position, right? How wherever we moved it, maybe it didn't move, but wherever it is after we've done the move routine, we know where it is in the Y direction, and so we can just return the load for that value. But what does the logic look like for rolling north? So I'll explain this because we'll use a similar algorithm in part 2, but the idea is we actually want to do a range, right? We want to go from maybe the best way is to show it. It would make more sense. If I'm at this one, if you think about the range that you potentially want to look at, it's right here all the way up to right here, right? Oh, I take that back. It's not all the way up, right? The range you want to look at is from right here to right here. And why is that? The check we're going to do, at least that I did, was I said, is the step or is the position above me vacant? And if it is, I move up, right? I don't want to do that up here, and that's why I start at 1. I start at the 1 position, because if once I check at the 1 position, that's actually checking if it's vacant up here, and if it is, I will have moved it. So if I check also at the 0 position, that would put me out of bounds, right? But notice I also want to do it in reverse, right? So so this is 0, 1, 2, and 3. I'm starting at 3 and then checking if 2's open and moving it there if it is. Then I go to 2 and check if 1's position is open, and if it is, I move it. In this case, I don't. But notice I'm going in reverse. So that's why I have the 1, 2 equals y, right? So in reverse, I'm doing the reverse order of that, right? So this is going to give me these values, 3, 2, 1, this thing, and that's what it's going to check for me. And again, I just go through the algorithm like I normally would, as I say, hey, is the position above me a block or a rock, I should say? If it is, we're done, so we can break out of this loop. If it's not, I'm going to make the position above me now the O, and I'm going to make the position below me a dot, right? That's the gist of moving it up. And then I'm going to update my position, right? I now know I've moved, so I need to update my position and move myself up. So again, just one more time, imagine I'm using this rock right here. The values that I want to iterate over are these values right here. And then how do I want to iterate over them? I'm going to start at this position at 4, and I'm going to say, hey, is the one above me available? If it is, I move this up, make it a dot. And I try it here too. Is this one available? Move a dot. Eventually I get to 1 and I say, hey, is the one up available? And it is, so I move it here. And so that's gotten me all the way through it. And that is essentially it for part 1, right? So again, to reiterate, essentially what I'm doing is just going through the entire grid. I'm calling that roll north function, moving them all up. And then as the way you do that is you just say, hey, look at the position above me. Is it available? If it is, move myself up. And I do that until either you hit the top or you hit some rock that's above you and you stop at that point, right? And then you can just calculate the total value based on where those rocks' positions are when you stopped moving them. And so if I run it, you can see here's what I get for my output for part 1. It's some relatively large number like this. That's because here's the example grid. The actual grid is substantially bigger, right? And so a lot of these rocks are going to go up quite a bit, and their values are going to be substantially higher because the total grid length is longer. But that was it for part 1. It's not too tough, right? I guess I explained it in about 10 minutes or so. Not too hard to solve. You just have to make sure you're thinking about these in the right order. Where part 2 changes is it says, hey, you know what? Moving it north worked, but you want to it turns out what you also want to do is what you're trying to do is like adjust a parabolic reflector dish, right? And he says, and so they're thinking like, hey, what you should do is move it north and then move it west, which I think is this way for you guys, and then move it south and then move it east, right? So now instead of just a roll north function, you need to have a roll for each direction. And what it says is do those rolls in each direction, and that will count as one cycle. And you said, oh, when I'm reading it, I'm thinking, oh, that stuff is not hard. I'll show you the roll north, west, east, and south, the new ones that I used for part 2. That's not too hard. And but then it says, you get down here, you should do that 1 billion times, right? So 1 billion times. When you see something like this in anything, right, especially in these Advent of Code challenges, a number like that should always instill in you there's got to be some other way. And if you've done Advent of Code before, there is almost always a cycle problem. And so that's where my mind led to this is surely I can't do this 1 billion times. Can I go through these cycles and find some kind How do I say that right? Can I go through all these cycles and see if I can't find a cycle within the cycles? That's a weird way to say it, but the way to think about it is, can I track the state of the grid, and if I ever see that state again, I can assume I've hit a cycle, and that was my solution to it, right? The idea being, and you can think about this in your head a little bit, but if a grid is ever in the same position that it was before, you now know some period that repeats, right? If it was in this position here and then this position here, you know that you're always going to get back to this position, right? So it always kind of repeats that way. And so once you've found that, you can kind of do some math to figure out, okay, well, I know my cycle is this long. Can I extrapolate what it would look like after a billion, right? And so I'll show you how that works. But I do want to say, after I solved this, I went and looked at other people's solutions, and I think some of them got lucky or maybe kind of just stumbled upon the answer, because the cycle finding we're doing here is actually not the same as cycle finding in graph theory. So I saw a lot of people that said, or I saw some people that said things like, oh, it was cycle detection, and they just look for a number that repeats. Like, can I find a number that repeats? And maybe that worked for this problem. That's possible. And I don't want to like belittle their solutions, because obviously getting the right answer is the goal. But all that being said, if you're looking for a number that repeats, like one of the examples is Floyd's algorithm. There's also a what is it called? Distinct set union or something like that. I know I'm getting this wrong. It's disjoint. Sorry, it's a disjoint set union. These are algorithms you can use to find cycles. They're meant to find cycles in nodes, though, right? And that's what, think about it this way, right? Is these nodes are like unique values, and they each all have like some kind of like edges that attach that you can traverse to get to another node, right? And these are mainly used to find. You could potentially do this with Floyd's algorithm, because it uses set theory, but it won't work in cases where the numbers repeat, right? It only works where the domain of your function, I'm probably saying this wrong, and I'm sorry, math wizards, is a distinct set. And so you can run into issues where you think you've found a solution and you actually haven't. So it does work for, these do very much work for these like network things, these nodes, right? Like you can imagine if you're doing this, the Floyd's algorithm, for example, you're kind of jumping around to these, and eventually you'll see like the tortoise and the hare will both land on this point, and you'll say, oh, I have found a set, or I have found a cycle, because the slow moving one and the fast moving one ended up in the same node. That doesn't work in this case, and in particularly in the test case. If you tried Floyd's algorithm on the test case, that is using this one right here, the array looks something like this. I don't remember exactly what it is, but it's like you have like 98 first, and then you have like 67, and then you have 69, 69, 65, 68, 67, and then it repeats like right here, right? But Floyd's algorithm, if you aren't implementing it in like a node style, would actually find these two values and say, oh, I found it. The cycle starts at 2 and its length is 1. So that's just a gotcha. I just wanted to point that out, is like, if you actually wanted to use one of these algorithms, you could. And the way that you would do it is you would turn your vector into a set of nodes, and you would, well, that may not actually work either, because you don't know if the nodes are you don't know what direction that, in the case of turning a vector into a list, it just becomes a straight line. So now that I think about it, you may not actually be able to use these algorithms. If you're smarter than me though, and you have a way that it actually works, I would love to see it. But I know for sure these type of things don't work when you have like values that can repeat within the sequence, as in to say, like, the next number here would be 69 and then 69 again. Because you have this repeating set in here, you have to do some very special logic to get this to work. And it may be that you just stumble upon the solution. That's okay. Again, you might think this, but a lot of these, I guess just what I'm saying is, a lot of these algorithms are like node-based algorithms. And so you need to make sure you have like unique nodes in here for the stuff that you're doing, right? And this problem doesn't lead itself to that if you go for, I should say is, it doesn't work if you're going for the total load, right? These are the total loads at each position at each time. Instead, the way, okay, so that was a lot of explanation, and it was mostly to say it has to do with the total load. So these set theory things in the graph traversal cycle finding does not work when you're doing total load, right? So if you just say, I'm just going to keep all the total loads and I'm going to get a list, I'm going to just track them and see when I found another one, these ones won't work, because the idea is the value should be unique, right? This one might be 69 and this one might be 69, but they are different nodes. And so the Floyd's algorithm and the other ones, they actually would find the cycle, and they would know that the cycle starts here and the cycle length is 3, because it's not concerned with the value, it's just concerned with the current node that it's on, if that makes sense. Hopefully I described that okay. Where this cycle finding does help though is if you think about the state of the grid, right? So if we go back here, kind of as I had mentioned earlier, and you kind of track the state of the grid, and you say, hey, if I've seen this state of the grid again, I know I have found a cycle. And in that case, you actually don't need to use these algorithms, because you're kind of building the grid, you're building this as you go. And so you really only, if you think about what you're doing, is you're building a node for a grid, and you're putting it at position 0. And then you're doing your roll routines, and then you're going to create a new grid at position 1, but you're going to check and see if I've seen this position before in there, right? And if you haven't, you know you're okay. So let's see, it's a hashing function, right? So let's say this returns A, this returns B from your hash. You know you haven't seen it yet. Then you're going to do the roll again, and B is going to turn into C, let's say. So you know you haven't seen that. And you can think again of these as nodes that connect like this. And let's just do one more. There's a D over here. So C produces D. We know that if you go from C and do the roll, you produce D. And then when you do D, if you produce B again, say D produces B, you know you've found a cycle, right? Because B is going to produce C, C is going to produce D, and D is going to produce B again. So you don't actually have to use an algorithm like this. Where an algorithm like this would be helpful is if you don't actually know where you're going this way. All you actually have to do is keep a set, which is what I did, of these hashes, right? And so you can actually literally use a hash set in Rust, or what they call it a set in Python, right? Other languages use some kind of hash set and say, okay, I'm just going to keep track of all these values, and if I ever find a previous value, I know I found my cycle. And this will tell me where my cycle starts, and then my position that I was working on before will tell me how far it goes. So now I know my cycle length. Okay. I hope I've explained that okay. My little weird foray into the graph theory stuff may have messed it up, but if you're not familiar with graphing, I think you can still grasp this idea, right? Is if you know if you happen to have seen a grid before that you've already processed, you know that you'll always get back to that grid. You know you've created a cycle because the work that you do is always the same, right? The work that happens right here to go from B to C is always the same. And so if you've found a cycle, you know that that work will always cause this cycle. You're now forever stuck in this loop. And so it's just a question of finding that loop. So how does that look in code? Sorry, that was a lot of explaining. What I actually did was I changed it up a little bit. So in part 1, I just had a couple functions that solved the problem. Now that I had an actual grid and I wanted to do some stuff on it, I created an actual structure. Notice I did the hash and the equal partial equal. That I'll show you that in a second. That's actually useful for the hash set. But I use my parse thing just to, so given an input, I do the same parsing as I did before. Here's where I now calculate the total load, right? And so how do I do that? And why do I do that here? Because as I'm going through the algorithm, I'm actually not interested in the total load. It's only once I've found my cycle that I need to finish through the cycle. And then I calculate my total load. So it doesn't make sense to calculate the total load while you're trying to find the cycle. So how do I do that? You can think of, again, I'm just basically doing an iter enumerate and then an iter enumerate. And if I find an O, I'm going to calculate its total value and I just sum all those up, right? If the functional style of this is a little confusing, you can just think about it as 2 for loops where I look for the O, and if I find it, I can add some value. I can calculate its load value, and then the total load is just the sum of all those I calculated. The roll north doesn't change much at all here because I'm basically doing the same thing. The only difference being now I'm doing it on the actual grid itself. So I'm updating myself. The roll east, so think about how these rolls changes really quickly. If I go back here, whereas when I was rolling north, I was always interested in these values right here. When I am rolling, what was the last one I was doing? When I'm rolling east, I'm interested in these values right here. So the logic itself is the same, where I just say, hey, if my next position, for example, in roll east is one of these, I know I'm done. Otherwise, I keep moving. That logic is essentially the same, but now the values that I'm interested in have changed from here to here. So all that's really different between all of these is this range right here has changed. So for roll east, I'm interested in this range. For roll south, I'm now interested in this range. And again, I may not necessarily use all of the ranges, but this is the area I'm interested in. And then finally, roll west, I'm interested in these ones, right? So those are the things that I'm going to find interesting. I'm do that. So again, these are all basically the same with just the range operator and then the next value I'm checking being different, right? It's either +1 if you're going down, -1 if you're going up, that type of thing, right? So these don't change much. And then I created a helper function to do the roll all, right? Because if you think what's happening in this algorithm over here that I've been explaining, I'm actually going to do a roll all here, a roll all here, a roll all here, and I'm just going to be doing that over and over again. So instead of putting all of that in the loop, I just create a roll all function. And what does it look like? This is fancy Rust syntax for saying, hey, go through each of the grids and go through the roll north and roll west function And for each of those, we want to do top left to bottom right. And then I just call either roll north or roll west, right? Doing it in this order is important, right? You wouldn't want to do these functions in here because you want to do all of roll north first, and then you want to do all of roll west second. And again, they're going from top left to bottom right, so that's why you see this happening here. When you're going south and east, like I had mentioned earlier, so it's the same logic as up here, but now I'm doing it in reverse. And again, why am I doing it in reverse? If we go back here, we want to make sure when we're going down, we've pushed all of them down already, right? So like if I'm going top down and here's my grid, if I'm trying to push this one down, my algorithm would think it's all done, right? Because it's like, oh, I can't move, there's something in the way. Instead, if I've done all the rolling this way, this one has now come all the way down. So this one has moved down here. And now this one knows that it can wiggle its way all the way down to here, right? So that's really just the difference between these two for loops. For north and west, we want to go from top left to bottom right. And for south and east, we want to go from bottom right to top left in reverse, right? Moving backwards. So that was the kind of the grid structure that I built for part 2, just to like simplify the function you'll see in a second. There's one last thing I had to do though, and that's this code right here. I wanted to be able to track the state, right? So in here, I'm interested not only in the grid's hash, A, B, C, or D, but I'm also interested in where it was when I calculated it, right? Kind of an index. So you could potentially do this in an array. What you'd have to do in the array is call like a find function in the array. So can you find, your array would look like A, B, C, D, and then you'd have to just say, can I find C in the array? And potentially, I mean, if it's small, that wouldn't be an issue, but it wasn't clear to me how big the cycle would be. And so I did it as a hash set. And so the way you do that is you track your state here. And so you have the step that you did it in, and then the original grid. And all you need to do for the state is implement to make it like hashable. We're not interested in the step for the hash, right? If we want to say, have we seen this before? We're only interested in knowing if the grid is the same. So for our partial equal and implementing partial equal and implementing hash, you notice the partial equal only takes the grid into account. We only say if my grid is equal to the other grid. The same thing with the hash function when we're hashing it. When we want to hash the state, we're only interested in hashing the grid itself, right? So I had mentioned I implemented hash in the grid, and so I call self grid hash on the state to get me to where I need to go. Okay, so now how do we solve part 2? You can see I basically do the same thing in my main as I do part 1, except instead of just using the grid outright, I now call grid.parse to get it, but I just call this p2 function right here, right? And so let's talk about what it looks like. It's actually not that complicated once you understand what we're doing right here, right? The idea is we want to track the grids we've seen before, so we create a new hash set, and then we're just going to iterate from 0 to a billion or 1 to a billion. We're hoping we don't have to go that far. We're hoping there's a cycle, right? So I said a little bit of a prayer when I was trying to, once it actually worked, that it would, I had bugs that I had to fix, right? But my hope was once it actually worked, it would happen relatively quickly. And what do we do? What are the steps? Well, let's add our state to our grid, to our scene hash set, right? So put our current position in there. And then we perform our rolls. And then we ask ourselves, is the new grid in the stuff that we've seen before? And if it is, now we found a loop, right? We found a cycle in the thing. If it's not, we just continue, right? We're going to do an insert and roll all. And this will happen, I don't know, I think it turned out I guess I could calculate these values again, but I think it found a cycle in like the first 200 or so for my input. So it only has to like do this roll all like 200 or so times, and you do all these inserts, and eventually it says, oh, I've seen a grid that existed before, right? And again, just to clarify what that means is I've seen the actual grid. It's not that I've seen the total values, because that's not going to help you. It's that I've seen the actual grid. So if the grid hashed to B, what that's saying is, oh, I found a cycle where I'm hashing back to B. So what do I do when I've found that same state again in a previous iteration? Now I can do some math, and it's right here in those next 3 lines, to figure out how many times I can do that to get to a billion. And the way to think about this is the modulo operator, right? You had to do a little bit more math than that, but at a high level, if you think about once you've found a cycle, you know you can do that cycle a whole bunch of times without actually calculating it, right? So if the cycle length is 20, you know that that billion, you can just do it, what is that, 500 million times? No, 50 million times? No, 500 million times, right? You know you can do, is it 50 million? Someone in the comments tell me what it was. But you know that you can just skip through all those times because they're all essentially the same. And so what does that math look like? Well, first we want to calculate the cycle length. And that is my ith position, like where I'm currently at, +1. And why +1? Because I know the cycle starts here, but the initial position of the cycle is the next one, right? And so +1, I'm going from my current position to the beginning of the cycle, which is right here, minus the number of steps, right? The state step. So where was my initial position, right? What that's essentially going to do is, if you think about it, it's going to put you in the Cth position, right? So if it's 1 and 3, we do 3 plus 1 minus 1, right? 3 is this value, 1 is this value. The +1 is to push us forward, and that gets us to 3. Did I do that wrong? 3 plus 1 minus 1. 3 plus 1 minus 1. Oh, it gets us right here, right? Oh, yes, that's right. We want to do it here. Sorry, I said that right. We want to do it here because what we want to do then is start the cycle over again for the next iteration. So that will get us that will get us the cycle length. So I may have been saying that wrong. I'm sorry. We want to determine the cycle length, right? And it's from this position to this position minus 1. Or +1, right? 3 minus 1 is 2, but the cycle is 3, so it's +1. This is the part I was talking about where you actually minus 1. You want to determine how many, from the billion, how many you have left to process. And so you want to subtract your cycle length -1. Essentially what you're saying is, I want to cycle through this as many times as I can, but I've already cycled through some of them, right? I was at this position when I found my ith position, and so I've already done that many calculations of the billion. So now I just need to know how much is remaining, and it's that value modulo the cycle length. Did I explain that very well? Maybe not. I'll try one more time. The way, again, at a high level, what you want to do is you want to find the cycle length. Then you want to find out how much you've already done of the billion, which is this. And you want to, and then you just do the modulo of this value to the cycle length. And that tells you like how much you have left to do to get into the, to get to the end of the cycle. Maybe the best way to describe it is if we create another one of these. I feel like I've made it harder than it should be. Assume like this is your 0th position and this is your billionth position. If you're right here and you found a cycle that's right here, right, and you found another position, you now know like these, you can repeat this process a whole bunch of times, right? So you're going to repeat it and it'll move you to here, to here, to here, to here, to here, to here, so on and so forth. These are all just the modulus operations, but what's going to happen is you're going to fall right here, and then your next one will take you to right here, right? And so there's this like little remaining part, right? You don't want to step over 1 billion. You want to stop right here and then just calculate the rest of this portion on your own. I hope that's a better way to explain it, and you understood it. Maybe you understood it the first way. Just didn't do a good job describing it, but that's the essential math you're trying to do, right? So here we're calculating the cycle length, and then here we're determining that what is remaining, right? So we're taking like this from this value to this value to see what's remaining, and then we do the modulus operator on that by the cycle length, and what that returns us is this chunk right here. And so now we know we just need to call roll all for the remaining of them and return the grid total, the total load. Okay, so how does that, let's just run it really quick. You can see it actually doesn't take long. If you went and maybe you did some printfs in here, you'd see that it found it in, again, it was like a couple hundred that it took for me to find it. But the algorithm actually isn't that hard. You're essentially, you're creating your own graph, and you're looking for the point where one of them eventually come back to another graph. And you're interested in the grid, right? What is the state of the grid? Do I ever go back to another one? Once you've found it, then you know you have a cycle, and you can kind of extrapolate. You can, like, another way to think about it is you're just deleting all of this work. You're saying, hey, I know I can, all of this work just is part of this cycle. So all I have to do left is what's left to get me to 1 billion. And that is what this math does. Again, we're using a hash set to track it, and we're using this state to put it into the hash set. And we just do something special where, because we're only interested in the grid for hashing to determine equality, we use these partial, equal, and hash implementations. So the hash set will tell us if state scene.get actually returns a value. Okay, deep breath. That was it for day 14. And again, it was, I didn't think it was too hard, but I don't want anyone to get the impression that I didn't struggle a little bit. Part 1 was pretty easy. I think I did part 1 in like, I don't know, 10, 15 minutes. It's just, if you're familiar with programming, it shouldn't be too hard to just loop through all of them, push them up, and eventually go there. This is one of those problems, though, where you will see this in Advent to Code, but also other places where they have multi-part questions. The first one sometimes is just kind of a stepping stone. No pun intended, but to the actual problem that they want you to solve, right? And so part 1 is just, can you figure out how to do this roll and total load function? Because I'm now going to ask you to do something substantially more complicated, and I want to make sure you have that working before you move on to part 2. And part 2 is a little tough, but again, when you see something like this, just keep in mind that there's got to be something up. There's sometimes it will be a math one, which those are the ones I'm the worst at, because I have taken, upper level math classes and stuff like that, but a lot of them are like set theory things or computational things that I just don't know about or don't remember. And so, like, there'll be ways sometimes where you can do math that says, looking at, K and N and D, it turns out that this is modulo, V, and so you only have to calculate it 1,000 times as opposed to 1 billion. This one wasn't that, though, right? This was, in my mind, the answer was clearly a cyclical thing. Can you find a cycle within the data? And then can you use that cycle to help shrink the billion down? And again, that's just what we did here. So there you go. That's my solution. I'm curious how you guys solved it. Maybe you found a better cycle detection. I apologize if my description of this graph stuff didn't help. I do, though, just to be clear, like I looked at some code and some people were just using Floyd's algorithm on like the total load calculations here, and it wouldn't work for me, at least for my input. Maybe it did work for their inputs and that got them to the problem, and that's cool. But it didn't actually work for me because they would have found cycles like size 1, which would have been no help to you, right? The goal would be to try and find a larger cycle. Maybe you could do Floyd's algorithm over windows as opposed to values. I don't know. That would be, if you did it that way, I'd be interesting to hear. But the disjoint set stuff, all those things are more like graph related. And if you think about it, I did use a graph. I just didn't have to do these because I would know immediately when I found a set. Where these algorithms are helpful is if you already have the list, but you don't don't have a pre-constructed like scene list. So you're trying to figure out what that is. And in this case, because I would know immediately if I'd found a previous solution, I didn't have to use an algorithm. I don't want to give you some misimpression that I don't think these are like bad algorithms, because they totally work for their intended use case. I just don't think they were necessary here. Maybe if you like calculated the first 1,000 of them, and then you wanted to know, is there a cycle in these 1,000 hashes of my grids? That's where these would be useful. And so if you solved it that way, that's perfectly fine. But again, what I saw some people doing, they probably just got lucky, is they use something really simple to say, hey, have I just seen my total load before? And I don't know how you got that to work. So there you go. But I do want to say, I don't want to belittle those solutions if I haven't said that before. If you can solve the problem with whatever code, I think that's awesome. And so by all means, you can look at my code. It is not the best. My solution is not the best. And I didn't do it in like some super fast time, right? If you look at the leaderboards, I'm doing this at, what does it say? 1826. So the leaderboards have all been solved for like, I don't know, 20 plus hours, probably. So there's much smarter people than me. And so my intention in saying this is just not to belittle people. It's mostly to say, hey, if you're struggling, don't look at the total load. That's not actually going to get you to the solution. You want to track the grid itself, right? The grid is the thing you're interested in finding, that have I seen it again? And if you do that will help you solve the problem. So there we are, day 14. A lot of fun. Again, I'd love to see your guys' solutions. Go check out the Reddit when you see this come up, and send me your solutions there. You can private message me them if you don't want to put them up in the mega thread. But I'd love to see your solutions, however you can send them to me. And obviously, if you have any input, let me know how they look. I'm always open to criticism. I know I could do better. So there you go. See y'all for tomorrow.